Differentiating sums turns out to be pretty easy. The derivative of f plus g is f prime plus g prime. Products are a bit trickier as we have to use the product rule, but at the end of the day, it's not too bad. But exponents, where a function occurs in both the base and the exponent, well, we have no idea how to handle that. So we need to be a little bit more clever, and that cleverness involves recognizing that the logarithm reduces arithmetic complexity. What I mean by this is as follows. We have two important identities for the logarithm. In the first case below, notice that we have a product on the left-hand side, which reduces to a sum on the right. The other identity is similar, where we have an exponent on the left and a product on the right. So this says that if we apply a logarithm to a product, we can turn it into a sum, and a logarithm will turn an exponent into a product. Since logarithms are pretty easy to differentiate, right, their derivative is just 1 over x, then this ends up being a fairly small price to pay to make the derivative calculation simpler. And one final note before we start the nitty-gritties, if you are given a differentiable function f and need to find the derivative of ln f of x, then we just apply the usual chain rule to get the following. And it doesn't matter whether f is some abstract function or a concrete function you're actually trying to differentiate, this is a useful formula to remember. Okay, so the best way to learn about what I'm talking about is to see an example. Here I'm going to write down a monstrosity of a function, and we're going to differentiate it. Now, of course, you could do this using the product and quotient rules, and you should try that, just so you can see how terrible it is. We are going to be more clever than that. So let's start off by taking the logarithm of everything. Don't forget to also take the logarithm of the f on the left-hand side, since this will end up being really important later. Now, I haven't done anything at this point, so let's expand this out using our first logarithmic identity above. This big product, in turn, becomes a large sum, where everything in the denominator picks up a minus sign. While we're here, let's simplify this a little bit more, pulling out the exponents whenever possible. So this is our most simplified state, and now we're going to differentiate. Again, don't forget to differentiate that left-hand side. We found that the derivative of ln f of x is f prime of x over f of x, so I'll put that in here. And the derivative of the right-hand side doesn't end up being too bad to compute. Now I want to solve this for f prime of x. That's what we're after, right? So by moving that f of x over to the right-hand side, we'll be done. But we know what f of x is. It's our original function. So I'm going to multiply this answer by our original function to get our final answer. You can try simplifying this further if you like, but personally, I don't think it's worth it. So this computation was a bit long, but it was relatively straightforward. And that's the price of logarithmic differentiation. We are trading complexity for length. Next up, let's try one of those exponential problems. Let's differentiate x plus 1 to the power of 2x. So it turns out we're going to do exactly the same thing as we did in the previous example. We start by taking the logarithm of both sides, again remembering the ln f of x term on the left, and simplifying as much as possible. Then we differentiate. Again, f prime of x over f of x shows up on the left. On the right, we're going to need to use the product rule, but that's not too bad. And once again, we are solving for f prime of x, and we know what f of x is. So we're just going to multiply that in to get our final answer. So logarithmic differentiation allows us to turn complicated derivatives into simpler calculations, and lets us differentiate exponential functions in the first place.